Okay, firstly, it's an honor to be here, and I appreciate the invitation a great deal. This is a work always in progress, and it is, at this point, it's 2 years old, and a lot of you have seen this, so I'm sorry if I'm a little bit repetitive on some of the topics. Okay, first of all, I'll talk about the motivation for GyPSuM and talk about our previous work, which gives kind of the sequence of events to get to the point of developing the model. And I'll talk about how we developed this model and discuss some of the observations that I see are very interesting from the model. And I'll give a really brief summary of it. Okay, so the motivation for joint seismic geodynamic modeling is we know in general that if you combine different types of data, you can reduce the non-uniqueness of a solution. And imaging the Earth is extremely non-unique, so the more types of data that you can put towards that image, the better. And we can also predict heterogeneity where seismic constraints are very weak if we use geodynamic information as well. We need detailed density anomalies in the Earth. And this is a step towards that. I don't think we're there, probably just the very beginning stages of it. But we need density structure of the Earth to understand the Earth, the evolution of the Earth, and to, in a practical sense, to calculate flow. You can't calculate flow if you don't know what the density is. And we also know, based on our previous studies, that scaling a seismic model, the model produced solely with seismic information, is inadequate because it doesn't fit geodynamic observations. And so it's hard to see how much you can actually learn from a pure seismically derived model in terms of flow. With joint seismic geodynamic tomography, we can solve for density directly. And we can, of course, evaluate the relative behavior of different properties of the mantle if we solve jointly. So to go through a little bit of the history, we have to first, in order to do joint seismic geodynamic imaging, we have to determine a few first-order problems, or at least address them. And one first-order problem we addressed in 2006 is whether or not the mantle flows as a whole mantle style or has strict boundaries to flow. So we solved for the joint system of seismic and geodynamic data with these assumptions, either with a strict boundary or not, and to see how well we can match the data. And we found that with a whole mantle style of flow, we could match the data better with all the cases that we tested. After that study, we were more interested in trying to figure out what compositional anomalies might be in the Earth, and particularly in the mid-mantle. What we found by separating out the compositional and thermal effects that we found entrained dense material in the mid-mantle of the African superplume. So this is material that's been swept up into this upwelling, and it's compositionally distinct material. After which we're looking at, okay, well, what is really the effect of joint seismic geodynamic modeling? And really what this boiled down to, if I blow up this image down here, what this really boils down to is that we can create a simpler Earth structure, one that you don't need nearly as much compositional influence to model all of the data simultaneously. And I'll touch on that a little bit more once we get into the new model. So these models that we've been producing are used for flow calculations, as I've said, by my colleagues Alessandro Forte, Robert Mucha, and others. They've led this work. And we focus on two areas primarily, North America and Africa. Beneath North America, we can see the Farallon slab sinking down into the Earth. But what's actually more interesting about this is that there's return flow on the western side. So this return flow coincides with the Colorado Plateau in the western U.S. and could actually be the source, or one major source of the uplift of the Colorado Plateau here. In Africa, we know that there's a large upwelling, the superplume structure. What we don't know is exactly how it connects to the surface, because in the present model, many present models that we see, we don't see a clear connection. We see a gap about at the upper mantle, lower mantle boundary. What we think is actually happening is that the superplume is flowing upward, and there are pulsing events of smaller plumes that come off the top of this structure and eventually reach the surface at the East African Rift. So I don't want to go into all the details of these geodynamic studies because I didn't lead those investigations, just part of them. But I want to point out one common theme, and that theme is that the large-scale mantle flow has signatures at the Earth's surface. So we are linking the large-scale flow to the surface of the Earth. That's been the common thread of all these studies. Okay, now I'll go into GyPSuM. First of all, what is it? The G stands for geodynamic, P stands for P waves, S stands for S waves, and M stands for mineral physics. And what it is a joint solution or a joint model of shear wave data, including multiples measured by myself and Steve Grand, and geodynamic observations, including global free air gravity field, tectonic plate motions in terms of the divergence of the plates, dynamic topography at the Earth's surface, and the CMB excess ellipticity, which is presumably flow-driven. And we also, one of the major differences between the other models is that we include P-wave data. And this is often referred to as the Harvard data set. And it's a fairly large set of summary arrays that many of you are familiar with, this particular data set. What we do is link these properties together, density, shear wave speed, and P-wave speed, through mineral physics constraints, at least broad scale constraints, or at least limitations of what these relationships should be in the mantle. If we have these relationships, we can create a very large system of equations to solve in the simple tomographic case. So we have to, first of all, relate geodynamic observations to structure. And many of you are familiar with this as well. This is the instantaneous flow concept. We represent different fields of the geodynamic data by spherical harmonics, mapped using viscous flow response functions to the density field, which is a combination of shear wave speed and the relative heterogeneity ratio of density to shear wave speed. And I should mention here that if we know what this ratio is, and we have thermally varying material or material that's being changed by temperature, we should have a pretty good idea of what the R-P to S ratio is. And so we tie those two together because of that. So in the first round of optimization, we use simple one-dimensional profiles of these scaling relationships, rho to S and P to S. And we define a range based on the work of Fabio Camerano and Corrado and Carchi, just to define a general range of what should be a thermal relationship between these fields. And we adjust these curves by amplifying or shifting. So we can change the shape and change the amplitudes of these 1D profiles, select it, create a global model using all of the data, and see which one's best. And we use a simulated annealing process to determine which of these curves actually fits the data the best. And maybe not too interesting, but the starting model is here, and the final solution is here. What I'm not showing in that relationship, or wasn't shown before, are these correction terms that we actually solve for at the same time in this optimization. So these correction factors account for the cratonic mass depletion, because we know the cratons can't be as dense as the shear wave speed suggests, and also the temperature dependence of Q, or the nonlinear effects, where if you have very high temperatures, this scaling factor should actually go way down. So going from there, we move on to full 3D scaling relationships. So now we're calling this 1D profile with the corrections the thermal relationship. So we move away from the thermal relationship to fully match all of the data, or at least match the data much better. And these are the distributions that of these scaling relationships shown here about the 1D thermal profiles. And what we see in the shallow mantle, of course, a very large distribution. There's two effects here. That's the cratons as well as the very slow ridges. And down in the deep mantle, of course, we see a fairly large distribution as well, a bimodal distribution in the P to S ratios. So with that, we create the GyPSuM model that is closest to thermal as we can get. So we allow, in that nonlinear inversion process, we allow the properties, the shear wave speeds, P wave speeds, and densities to decouple from what we expect for thermal variations. And so we get shear wave speed, P wave speed, and density, isocontours on the left of the full structure, and on the right is with the top 600 kilometers removed so you can see the deep structures. And what I should say is that we see these in all modern global tomography models, so there's nothing fundamentally new about seeing these structures, but the details have changed. One of the primary observations that we see is to follow on to what we've seen before, is that temperature appears to be the primary contributor to P, S, and density. So P wave speeds, S wave speeds, and density. And what I've done here is separate out the non-thermal component in terms of RMS amplitude of these fields with depth, and the thermal component shown in red. This is for shear wave speed. Clearly, temperature dominates shear wave speed. This is P wave speed. Temperature variations are always the largest contributor, but it's not nearly as dominant as with shear wave speeds. Density is primarily driven by temperature in our model, except perhaps in the very deep mantle. In terms of sound speed, because of the relative behavior of the bulk modulus and density, we expect that it's primarily variations in sound speed is primarily an indication of compositional variations, which has been observed for a long time. So another observation that we see is this decorrelation of shear wave speed and P wave speed in fast anomalies in the lower mantle. This is a cross-section through the Farallon slab, and this is shear wave speed here, and this is P wave speed here. And we've done everything we could to make these map one-to-one, to make this image look like this image, and they just don't. You can't do it. And so in other words, these structures tend to be muted in the P wave anomalies that we see, and we see this as a global trend. Now, you might say that is an indication of compositional anomalies, but we say that there are possibly other effects that are not compositional at all, rheological effects due to, and this is one example, due to electronic spin transitions within the iron-bearing mineralogies, which is supposed to occur maybe 1,100 kilometers to 1,900 kilometers depth, this transition. It's highly debatable at this point, but it just turns out that where this break is between these two structures is right here, right in the middle of where this is expected to occur, at least by some studies. Okay, another feature that we see that I find very intriguing, I finally wanted to point it out because we kept seeing it in our models over time. Steve Grand's original models, you can see very faint signs of this perhaps slab structure in the middle of the Pacific Ocean, and over time, each time we create a new model, this has gotten brighter and brighter and brighter. So I'm choosing now not to ignore it. Even though seismic constraints are very weak in the mid-mantle in the middle of the Pacific, we have geodynamic observations as well that help brighten this feature, I believe. And so it's very indicative of another subducted slab remnant in the middle of the Pacific. So we know if we go back about 100 million years ago, we know that there had to be at least 3 large plates, Pacific plate, the Farallon plate, and the Izanagi plate, with a triple junction somewhere in the middle of the Pacific. How far that could have been away from this example is probably highly debatable as well. But it's expected to be a ridge system, a triple junction of ridges. So this really doesn't make sense necessarily for that. If you go back even further, it's been recently suggested using interoceanic volcanic arcs that are currently on the up against the East Asia, the Northwest Pacific in the present day. It's been suggested that these could have lined up in a way to form a complete arc or a complete subduction zone somewhere in the middle of the Pacific, suggesting that there must have been more slabs, very large slabs, and maybe the Izanagi moved over this, and this slab subducted beneath the Izanagi and is completely gone as well. today. So this is very much in line with what we're saying, but it's in a different location. So there's a lot of work to be done to understand if that could actually be tied together. So the other aspect of this modeling, like I said, we can evaluate the relative behavior of properties in the mantle. And what I've done here is looked at the African superplume and do 3D maps of where properties are the same. And for example, in the very deep mantle, we see what I call the dense pile part 1. And this is low shear speed, high sound speed, and high density. So this is a large zone of high density, so it's a dense pile, even though our densities aren't nearly as high as others suggest. But that's probably due to the minimalization technique that we do. Above this zone, we have another zone that now has low sound speed. So it's hard to understand if it is high density, why is it low sound speed? And that might be a dense partial melted layer, or perhaps a differentiated material that's been superheated around this very large pile. Highly debatable. I'm just throwing this out there at this point. Above this zone is what I call the high entrainment zone. This is where we have low shear speed still, high sound speed, and low density. Of course, the high sound speed suggests that it has a compositionally distinct material in it, but overall it's low density. It's still slightly buoyant, but it has an entrained high density material within it. So overall it's low density, but the high density material is there. Another thing to point out here is that we don't see this in West Africa, where we have also these very large low velocity provinces as well, but it doesn't show up there. And that's been the basis for our argument that these features in South Africa and West Africa are separate. Because when you do map the 3D structure of low shear speed, low sound speed, and low density, now this feature starts to pop up. If we look a little shallower, rises up to West Africa. The South Africa rises up to the East African Rift and the Cameroon region. And if you look even shallower, it looks like it connects all the way into North Africa to the Hogar Plateau region. And it's interesting to note also this material here has a high density signature to it as well, even though overall it's low density. So that might actually be a fingerprint that this came from South Africa. So to give a quick summary, I'm pretty good on time. We've constructed a global scale joint seismic geodynamic mineral physics model, GyPSuM, and the approach, because of our optimization procedures, it's designed to map most heterogeneity into temperature variations, if that's possible. But then it has a residual component that cannot be explained readily by temperature variations. And except for the cratonic roots and parts of Deitable prime, we find that temperature seems to dominate the anomalies, or can be done that way with the data and procedures that we've used. And we've started with very broadly defined mineral physics constraints. Really the best constraints are the initial shape of the 1D profile and the range that we defined that suggests that should be thermal. So really it's really broadly defined. Future models should incorporate more recent and complete mineral physics relationships. But it should be mentioned that trade-offs are very problematic, because even if you think, okay, these relationships are better, you still have the effects of lateral viscosity variations, for example, especially when you go to very detailed models. The lateral viscosity variations become very important in the joint seismic geodynamic model, and these trade off directly with scaling relationships and seismic heterogeneity amplitudes. And I'd like to say that this model is available for download on the IRIS website. Right now it's the P and S wave anomalies, and hopefully density will be placed there soon as well. And that's all I got.